In this bonus video, I'm going to talk about the algebra of the Gaussian distribution integral, what if is called Gaussian integral a little bit. If you recall, the Gaussian distribution has a kind of a more difficult form, I may say, compared to other distributions that we have seen so far. And for instance, we didn't try to integrate this probability density function and show that this indeed satisfies the property that the area under the probability density function in the domain of X should satisfy 1. And in this video, I'm going to try to do that. And this derivation is due to Poisson. It has an interesting trick here because none of the transforms actually makes this integral possible to solve. But the trick with actually it's a very simple but very interesting, a very genius trick that Poisson came up with. It's possible to solve this integral. Then I'm going to talk about, or I'm going to show you how to find the expected value of the Gaussian distribution. So let's start with this one. Let's show that this is indeed fx for Gaussian distribution is indeed satisfies the probability density properties of the probability density function. Well, actually, it already satisfies the non-negativity of probability density function because exponential of here, this value is going to be always positive. It's going to be, non-negative. Therefore, what we only need to prove is this condition. So actually, if we write this integral here, oh, we hit square here, I forgot, sorry. And I'm going to integrate x from -infinity to +infinity. So first of all, I would like to transform x into z, so that we get rid of these parameters mu and theta. So I'm going to make this transform, which we already call transformation. So delta z sigma is going to be equal to delta x. So if I put it in the integral times exponential z square, and instead of dx, when I write the sigma, these sigmas will cancel, and we got this relatively more prettier form. You may also take this as the probability density function of a standardized normal variable, because a standardized normal variable has an expected value of 0. Therefore, mu is going to be equal to 0 here, and the standard deviation is going to be equal to 1. Therefore, the standard deviation sigma is going to be 1. Now the question, what is this integral? Is this integral really equal to 1? This is the question. Let's just concentrate on this region. Taking this as the integrand, we would like to show that the area under this integrand is indeed square root of 2 pi, so that when you multiply by reciprocal of square root of 2 pi, it's going to be equal to 1. So let's just concentrate on this integral. What is this equal to? Actually, here is the first step of the trick. This can be written as multiplication of the same integral. But what I do here is I use two different dummy variables. Note that in an integration, you can use any dummy variable. So it's just multiplication of itself and taking the square root, no big deal. But now actually we have already started with the trick. What we have done actually is we have specifically used x and y here. We have actually converted the question into 2 dimensions, into x and y plane. So what we do here is when you actually take this, and from now on I'm not going to consider square root, I'm just going to consider this region here, these variables here. So I'm just going to concentrate on these elements. Call this so in square root of s. Therefore, I'm going to be concentrating on s. So this is going to be from minus to plus infinity, and from minus to plus infinity, exponential x squared plus y squared dx dy. Now here is another trick, or another step of the trick. Note that these are x squared and y squares. Therefore, these are what we call even functions. Up to the value of 0, and after the value of 0, we have symmetry here. So we can write this as 4 times, or actually let me write that way, 2 times from 0 to plus infinity, and let this be related to y, because but actually I'm going to integrate y from 0 to infinity, and I'm going to multiply by 2. And I do the same thing for the x. Therefore, I'm going to be multiplying this by another 2 times. Therefore, the whole thing, the whole coefficient is going to be 4. So this is going to be 1 over 2 x squared plus y squared dy dx dy. So now here is the trick related with polar coordinates. I may say this is the main trick. Actually, this is the reason why we have done this whole thing. Actually, if these are the coordinates x and y at that point here, note that this can be in polar coordinates represented r as this radius and theta with this angle. Therefore, x squared plus y squared in polar coordinates is going to be equal to, if you write the polar coordinates as y is equal to r times cosine theta, sine theta, and x as r times cosine theta. When you take the square of both elements and add them together, the result is going to be r squared. So here is a very nice. Let me leave the integral bounds here, because we are now changing the variables from x to r. So it's going to be, I'm going to deal with the r in a couple of minutes. This turns into r squared. Now, what about dx dy? Actually, maybe you have seen this in fluid mechanics course or some mathematics course. I'm not sure about that. I hope you have seen. But even if you haven't seen anything like that, let me put here an additional note. What is dx times dy in terms of r and theta? So here is the idea. When we are talking about dx dy, we are talking about a differential area. So this is dx dy. Now the same differential area can be represented in polar coordinates in this fashion. If this is some arbitrary r value, right? And if we are talking about a very small d theta here, an angle, and again dr here. Now this distance at this point is going to be equal to r times d theta, because actually it's due to the circumference of the circle, r times 2 pi. So if you don't have the full circle, but if you have d theta, it's going to be r times d theta. And when you would like to find the area of this small square here, or small rectangular piece here, I'm sorry, it's going to be r times d theta times dr. Therefore, this is going to be r d theta dr. So this is going to be, I'm sorry, this is actually multiplication sign. This is going to be dA. When you equate those two, instead of dx dy, you may write r d theta dr. So our expression now turns into 4 times, let me use the black pen, and all right, let's see, minus 1 over r here. Actually, I could have just continued from that part, but there seems to be no place left. So this is going to be r times dr d theta. Now, what about these? Now, if we take this d theta and let's assume that this integral corresponds to d theta, note that where we have taken the integral previously, we have taken the integral previously from 0 to infinity and 0 to infinity. So therefore, in again xy plane, we integrate from 0 to infinity, and we integrate from 0 to infinity. So therefore, we are only interested, or we are only performing the integration in the first quadrant. So we have to do the same thing in polar coordinates. In order to describe the first quadrant, the polar coordinates, in terms of polar coordinates, is going to be, r is going to go from 0 to infinity, r, whereas theta is going to go from 0 to pi over 2. So this is going to be 0 to pi over 2 over all possible non-negative r values will actually cover the first quadrant. Therefore, here for theta, we write from 0 to pi over 2, and for r is going to be 0 to plus infinity. Now let's go one step further. Here we have still 0 to plus infinity, which corresponds to integral, but the limits of r is going to be r dr from 0 to pi over 2 d theta. Note that these terms are not related with d theta. Therefore, I can take this integral here and just put it here. Now, that's very nice because we have now product of two separate integrals. This is going to be equal to simply pi over 2. And let's deal with this one here. This is going to be, note that although it seems a little bit complicated, well, I have forgotten r square everywhere here. Here and here, I'm sorry. This is going to be basically very simply, if you take the derivative of 1 over 2 r square, note that it's going to be equal to 2 r's, and when you multiply with 1 over 2, they are going to cancel each other with a negative sign. So there's going to be an r here. If you just put a negative sign, this is going to be the integral of this quantity. So we are going to integrate it from 0 to infinity. So we have also 4 here, and we have also pi over 2 here. So when you put it infinity, it's going to be 0. When you put 0, it's going to be 1. But there's minus sign here, but we also subtract the whole thing, so it's going to be 1. So this whole thing is going to be equal to 2 pi. Now let's see where did that came from. This came from, actually, this is the value of what we call s here. And this was actually the integral that we were interested in, was square root of s. Therefore, this quantity is equal to square root of 2 pi. Now let's go up. This square root of 2 pi is, when you here and when it cancels with square root of 2 pi, and the result is going to be equal to, actually these will cancel each other, and dz is going to be equal to 1 here. So therefore, this is going to, this completes the proof. Okay, since we were able to find the integral of this question, which was exponential minus z squared over 2, this was found to be equal to square root of 2 pi. One may tend to think that we can find the probability distribution, cumulative probability distribution function, or any probability related to a region of a Gaussian distributed random variable, which means actually solving this integral. For instance, probability of z smaller sum, z value, which is basically equal to the cumulative distribution function of z, and we show it with phi z, which is going to be equal to integrating from minus infinity to z, this integral. And let's call this x squared over 2 dx 1 over square root of 2 pi, which is just a constant. And this is a standardized normal distributed random variable with 0 mean and one standard variance equal to variance unity. Now the problem is, unfortunately, this integral doesn't have a solution. That may seem strange, but actually This, let me put it that way, no solution. What do I mean by this? Consisting of a finite arithmetic operations consisting of exponentials, logarithms, constants, and solutions of algebraic equations. So unfortunately, this integral doesn't have a nice form. That's why what we, well, it is a little bit of above this level of this course, but what we call error function in mathematics is actually equal to from 0 to x exponential minus, this time let me call it again z. This be z, and this is going to be again z with x squared dx. Therefore, we use this error function to evaluate this integral. As you can see, it's not of the same form, but these are very close to each other. By just multiplying with constants, you can easily convert this error function to cumulative distribution function. So how do we find this solution? We find this solution by approximate methods. Approximate numerical methods are used to find this error function. And therefore, well, although the Gaussian integral can be integrated from minus infinity to plus infinity, and we can find the exact result. Therefore, we use it for a normalizing constant 1 minus 2 pi in the Gaussian distribution probability density function. Here, this 1 minus 2 pi. We cannot integrate this Gaussian, this probability density function around or between any arbitrary two finite values. And for that, what we use is an error function, which is computed using approximate numerical methods. So that's why we use the tabulated values at the end of our textbook or any other statistical textbook or other computer packages.